So welcome all. So today we are on another lecture. So here we will see how to design a one-way slab. Mainly it can be a isolated slab and or it can be a continuous slab. Okay. So we will see that. So first we will just draw a plan view of a slab. Okay. So we have drawn a plan view of a slab. Okay. So we are just drawing one reinforcement here. Okay, and another reinforcement here. Okay, now one thing we need. Okay, this. Okay, just draw it once again. Yeah. Okay. Thing. Okay, so let's see. This is a say a plan view of a slab. Okay, so this is mainly a slab. You can say it here that it is supported by all the four sides. Okay, so all the four sides it is supported. Yeah, so all the four side it is supported. So see what all thing we can see from here. This is the main bar. See, we know that in a one-way slab, let's say we have considered it as a one-way slab. So in a one-way slab mainly occurs the bending mainly occurs in the shorter span. So say this as Lx and this as Ly. Okay, so the shorter span is the Ly. So mainly the bending will occur like this. Okay, so the bending will occur like this. Yeah, so this will along we know that along the shorter span mainly we provide the main reinforcement. So this is our main reinforcement. Okay, so this one is our main reinforcement. See here, main reinforcement. Okay, and this green one is that is in the longer span, or you can say it as along the shorter span. So this one is our secondary reinforcement or distribution reinforcement. Okay, secondary reinforcement. Okay, so while designing a slab we always design it for a unit width. So you can take it as a note here. Note that is slab design is done considering a strip of unit width. Okay, so see it here, the slab, though this is the unit width we have considered. Okay, so this is the unit width, so let it be that this is 1 meter. Okay, This is 1 meter. Okay. So if we draw a cross section here, yeah, see, let's say this is the cross section. Okay, so this is the depth of the slab. So the depth of the slab is D, and this is the width, unit width. Okay, so this unit width is 1 meter. Okay, so this is a general concept. Now we are going to the steps. Okay, so one way slab design is mainly on unit width. You have to remember it that. Okay, so step 1. Okay, the step 1 is we have to assume a depth D. Okay, for preliminary design. So assume D for preliminary design. Okay, so after that what we will do, we will just do L effective design. Okay, so after that we will do L effective divided by D. This value should be less than K1, K2, K3, K4 into value. Okay, okay, so what are these K1, K2, K3, K4? We will see it one by one. So K1 depends on span. Okay, depends on span. So you can write it here also that up to 10 meter we take K1 value as 1. So above 10 meter, we take K1 value as 10 by span. Okay, yeah. So next we will see K2. So K2 is mainly, it depends on the percentage, depends on percentage tension reinforcement, so mainly K2 value also can be taken as 1, but by permutation combination, but by experience we have seen that if we take it 1, we have to redesign the depth will not be satisfied. Okay, so what we will do, we will generally in designing take the K2 value as 1.25 on preliminary basis. Okay, you can take it at 1 also, but for preliminary basis we are taking it as 1.25. Okay, so after that K3 is equal to, it is value is 1 for singly reinforced Okay, after that the K4 value is also 1 for rectangular section. Okay, rectangular cross section. Okay, rectangular, yeah. So everything is there. Now one thing is only left, that is value. What is that value? Okay, So see here this value, okay, from where we will get this value. So we are writing is as value. So what is it value? Mainly this value depends on the deflection control, okay, deflection deflection control, okay. So what are the value? This value, see this value is also having criteria, that is the shorter span, the shorter span should be up to 3.5 meter. These all are codal provisions, okay. And the loading or the live load, okay, the loading should be 3 kilonewton per meter square, okay. From here only you can know that it is a live load. So then this L effective by D ratio should be less than should be less than. So now the values we will write. So there will be supporting conditions, supporting condition, okay, and there will be two bars, fe 250 and fe 500, okay. So what are the supporting conditions? The supporting condition is, first, number one is simply supported, okay, simply supported, simply supported. Second one is continuous, okay. So second one is continuous. So see what will be the value. So for fe 250 the value is 35, and for continuous it is 40. For 500, what we will do, 500, sorry, 500 or 415, it will be same only, okay. So what will be the value? Just multiply it with 0.8, okay. The value will be coming to 28, and multiply it with 0.8, the value will be coming to 32, okay. Yeah. See, so this is the value. So this one, and this one are the values, okay. So see, after that what we will do, so from here this D you will get, and now calculate capital D, okay, by taking suitable effective cover, suitable effective cover, okay. Yeah. So next step will be, you have to calculate the effective span, calculate effective span. That is mainly the L effective calculation will be done here. Okay. After that, step 3. So what we will do in the step 3, see, you have to calculate the dead load and the design bending moment. Okay, calculate dead load and again calculate bending moment. Okay, if continuous, if the slab is continuous, use bending moment coefficient. Bending moment coefficient. So what are the coefficient? We will see it. Okay, if continuous slab. Okay, if continuous slab, use bending moment coefficient. Okay, so this bending moment coefficient we are seeing at last. Okay, yeah. Next step, step 4. Okay, so we have to calculate the D again. Calculate the depth again for balance section, for a balanced section. So how we will calculate the D for a balanced section? It's very easy. Bending moment ultimate is equal to mu limiting. We will limit the bending moment. Okay, so bending moment ultimate is equal to QBD square. This D we have to calculate. Okay, this is the required one. Okay, this is the required one. See, previously we have calculated the D. Okay, so this previously we have calculated this D. This D is the provided one. Okay, this D is the provided one. So one thing, see here B is equal to 1 meter or 1000 mm. Okay, so one thing is that D provided should be greater than D required. If not, then what we have to do? We have to again assume a D value and again repeat the step 2 and 4. Okay, so next step, step 5. Step 5 is that you have to calculate the AST. So see, if D provided is greater than D required, so section is under reinforced. Okay, under reinforced. So here we will calculate the area. AST is equal to 0.5 FCK by Fy bracket 1 minus root over 1 minus 4.6 mu divided by FCK BD square into BD. Okay, so this is the formula for calculation of the area. But one thing here also, this B, here B is also 1000 mm. Okay, now what we have to check, we have to check for the area, that is, now this is AST calculated, AST calculated, calculated, AST calculated should not be greater than greater than sorry, should not be less than, should not be, should not be, should not be less than AST minimum. Okay, so one thing here also, that is, for Fe415 the AST minimum value is 0.12% of cross section area. Okay, so BD, or the cross section area for Fe415, for HO, sorry, that is for HYSD bar. Okay, yeah, so now what you have to calculate now, this is step 5, step 6, step 6, provide reinforcement, provide provide distribution reinforcement, distribution reinforcement. Okay, and next step is step 7 is reinforcement detailing. Okay, so here the reinforcement detailing is a very big part. Okay, so we will first see it here, and next then we will go to this bending moment coefficient. Okay, so first we will see how to do the detailing. It is a little bit tough here. So this is the mainly, yeah, this one is the cross section of a slab. Okay, see here, this one is one support, and let's say this one is another support. Okay, yeah, so this one is one support and this one is another support. So we will draw here a break line. Okay, now we will first draw the reinforcement. Okay, so give me a little bit time. So this is the one reinforcement. Okay, so this one is the another reinforcement. Okay, so this one will be another reinforcement. Yeah, I think everything is completed. Okay, see here now. We'll take this black color only. Okay, so this one is the support. These two things are the support. Okay, so mainly from this center and from this support center, this is L effective. Okay, just from this center to this center, this one is called as L effective. Okay, now see here. See, mainly this bottom bar, the first see here, I will explain it. See, this is the bottom bar. Okay, so this one is AST plus. Okay, AST plus. Yeah, now near the support. Okay, near the support, see first do. Okay, and near the support, this one, sorry, say here this one. Okay, this one will be AST plus divided by 2. Okay, so now this top bar, just cut here one and cut here one. Okay, so now what we will do, we will just take it. Here it is AST negative minus. Okay, so here this one is AST minus by 2, and here also it is AST minus by 2. Okay, now this one is AST plus by 2. Okay, now we will just first take the distance. Okay, we will first look onto the distance. Okay, also cut here. Yeah, you can do it in black only. Okay, yeah, this one. So this mark, what we are doing with this black color, is the curtailment of the reinforcement. Okay, so this all things are the curtailment of the reinforcement. So I am explaining it. What is the curtailment, why we are doing it here. Okay, so let's first draw the distances. Okay, so from here the distance is 0.25 L. Okay, so from here also the distance is 0.25 L. Okay, so here also you can term it as AST plus, and here also you can term it as AST plus by 2. Okay, wait. Yeah, so again from the face of the column, from this to the face of the column. Okay, this distance is 0.15 L, and this distance, and this distance is also 0.15. Okay, wait. 0.15 L. Okay, and from here also, here to here it is, and here to here this distance are 0.15 L, and this distance is also 0.15 L. Okay, so this one distance is 0.15 L, and from this face of this column it is 0.1 L. Okay, so let's see. Yeah, I will just take a highlighter and tell you. Okay, see here. So mainly this is the main bar. Okay, so this is the main bar, that is we have written it as AST. Okay, we have written is a AST. Okay, so AST plus positive. Okay, so you just mind it as AST positive. So we will get the AST positive, we will give the value to here. See here, up to what value we will give. See, in the middle we will give it, in the middle like this we will give it. But see here, this is the curtailment being done. Here the curtailment is being done. So from this column, so this mainly from the face of this column, from this face of the column, this line is going. Okay, so this line, we here we will provide it as AST plus by 2. Why we will provide here the half the area? As because we all know that, see, we all know that for the bending moment, here will be, here will be the maximum. Okay, here will be the maximum, and from here it will be, here will be sacking, and from here it will again hog. Okay, so we are curtailment of the bottom bar is being done. Okay, I think it is now understood that the bottom bar requirement here is less. Wait, just I am omitting this. Okay, so this bottom bar curtailment is being done. Okay, just wait a minute. It's got deleted. Yeah, so it's back. See here now. So this AST2, you AST plus divided by 2, you can get it that we are providing the half of the reinforcement here. Okay, so the half reinforcement means we will curtail some bars. Okay, from here, so this area, the length will be from the face of the column, from the face of the column it will be 0.15 L. Okay, so this curtailment will be done. After that we will provide the AST, and again we will curtail from this support, from near the support we will take again a 0. From here. So see, this is the starting, this is a starting. Okay, starting of the slab. But here, but here what is, here it is a continuous na, here it is continuous. So here the length is 0.25 L. Okay, so again we will provide it as AST by 2, as because from here also we know that here also the sagging moment will reduce, here only the hogging will come. Okay, so we are curtailing the bottom reinforcement to half, means we are increasing the spacing. Okay, so see again here, after this support also we are providing ast by 2, as because it is near the support, so bottom reinforcement requirement is less, as because sagging is not coming. So here also the length is 0.25 L, and after that, if this is the continuous, we have not shown here, so see we have shown a break line here. So again we are providing as ast plus. Okay, like here we are providing it here also. Okay, now see one thing, that is this you don't get confused. Okay, this 0.25, this 0.25 is for a continuous end, and at starting it is 0.15. This is for the bottom bar. See, for bottom bar we are taking is just ast plus. Okay, see, now we are telling the top bars. Okay, so top bar, first what we will do, first this top bar ast, we will provide it as ast by 2. We will take this bottom area only. Okay, for this starting we will provide it as ast by 2. Okay, so how much length we will provide it, we will provide it for 0.1. Okay, we will provide this length for 0.1, 0.1 L. Okay, so see, the middle we have not provided here, we have not provided here any bar, as because we know that here only sagging will come, so the bottom bar is required here. After that, see, near the support, so near the support we have again provided, so near the support we have again provided our top reinforcement. So how we have provided, see, at the this in the middle of the support we have provided as ast minus, we have total provided the total area. But as, see, from this face of the column, from this face of the column to a length of 0.15 L, we have provided this bar. Okay, we have provided this bar. After that, what we have done, we have provided the ast. Okay, we have provided this ast only up till here, just up till here we have provided this ast minus. Okay, but after that again, for a 0.15 L we have provided ast minus. Okay, again to up to this length of 0.15 L we have provided ast minus. That means you can see it here, that from this length to this length we have provided ast. Okay, we have provided this ast, means this column length. Okay, and after that 0.15 L here and 0.15 L here, we have provided the ast minus. Okay, but after that also we have provided this thing, the ast minus by 2 and ast minus by 2. Okay, so this is the top reinforcement and this is the detailing. Okay, so you can just slowly go through it, it is a little bit complicated. Okay, now what we will see here, now we will go here. Yeah, we will go this to this one. Okay, if continuous slab, we will use bending coefficient. So what is the bending coefficient, bending moment coefficient, bending moment, bending moment coefficient for continuous slab. Okay, so let's see. So see here, we'll just again draw a slab. cross section of a slab. You, you can draw the supports. Yeah, so we have drawn the supports here. These are the supports. Okay, see. So this one we can, so we will draw a break line here, as because this is a continuous one, we will draw a break line here. Okay, so here, see here, this one is the end support. Okay, this one is end support. Okay, this one is the end support. So this one is next to end support. This one is next to end support. Next to end support. Okay, or it is also told as penultimate support. Penultimate support. Okay, so let here also there is a continuation of a slab. Okay, so this one is called as, so this one is called as interior support. Interior support. Okay, see here, just drawing for reference, it's not needed. Just take a reference line. Okay, like this. Now see, I am drawing a freehand as because it will be easier for me. See, from this one will come like this and meet here. Wait, okay, see here, so it's a freehand drawing. Just don't look at the figure. Okay, it's a freehand drawing. Yeah, so this is a bending moment diagram. Okay, this is the bending moment diagram. See one thing, there will be two type of coefficient. One is for fixed load, one is for non-fixed load. That is, non-fixed load is live load and fixed load is mainly the dead load. Okay, one is for fixed load and one is for non-fixed load. Okay, so see, I am just writing it in the bottom of this. Okay, see, it will be plus 1 by 2, sorry, plus 1 by 12 minus 1 by 10 plus 1 by 16 minus 1 by 12. Okay, so for non-fixed it will be plus 1 by 10 minus 1 by 9 plus 1 by 12, and here it will be minus 1 by 9. Okay, so these are the coefficient for the bending. Again, I'm not, I'm just drawing again a line for reference. Wait, so here take a line again. Okay, if I draw it, yeah, it will come here and this support will come here. Okay, yeah, so what will be done? So here it will be like this, it will go up in the middle. Okay, it will go up and it will end, not, will come here, and we'll draw here the break line. Okay, yeah, so this is positive, this is negative, this is positive, this is negative, this is positive. So what is this? This is the shear force. Okay, so we will see the, now we will see the shear force coefficients. Okay, so you can write it here, bending moment coefficient, and here it will be the shear force coefficient. See what will be there. Here also there will be two things, that is fixed load, and there will be non-fixed load. Okay, so it will be, here it will be 0.4, here it will be 0.45, here it will be 0.6, here also it will be 0.6. Okay, under this plus it will be 0.55, it will be 0.6, under minus it will be 0.5, it will be 0.6, and under this plus it will be 0.5 and it will be 0.6. Okay, so these are the coefficients. Oh, okay, this lecture is going very long, so another 1 2 minute. Okay, so for positive calculation, okay, we will do, we will do the numerical, all these things will get clear. For positive calculation, bending moment, see here one thing, we are taking some sections, like one section is being taken it at here, that is A, and one section is being taken at in the middle of the support as B, and one section is being taken here at the face of the support, that is C. Okay, so bending moment at A is equal to plus 1 by 12 WF L effective square plus 1 by 10 WF L effective square. Okay, so for minus calculation, bending moment at B means, minus means we are calculating at the support, that is for the top. For this bending moment, the respective area that will come, that is AST minus, we will give it at top, and for this the AST plus will come, that we will give at the bottom reinforcement. Okay, the respective area. So this will be, everything will be clear when we do the numerical. Okay, just I am writing the formulas. 1 by 9 W non-fixed, sorry, here one thing is, okay, that here will be NF, that is non-fixed. WF is for fixed and WNF is for non-fixed. Okay, and L effective we all know. Okay, and here the shear force calculation will be at the face of the column, that is, so C section, that is 0.55 WF. So here it will be L clear, as because from the face of the section, face of the column, so it will be not be L effective, it will be from L clear. So the 0.6 W NF not fixed, L clear. Okay, so this is the thing. So by using these steps and formulas, we will calculate our one-way slab design. Okay, for a unit width. So we are winding up the lecture here. Thank you.